Is it clear, my voice?
Oh, yeah.
Okay, good. Okay, so we just wait for the rest to join us. Okay, so I just took around 5 minutes. Okay. All right. Good morning, everybody. So yeah, we're going to start right now. Okay. All right, are you guys able to see the screen?
Yes.
Yes.
All right, good. So we're going to start. Okay. All right. Good morning, everyone. So, yeah, as for today, we are going into chapter 7, which is a physical database design. Okay. So for this lecture time, we will focus on lecturing, okay, for this chapter 7, physical database design. So bear with me, okay? So we're going part by part on this chapter 7. All right. So hopefully you guys are in a good way. Okay. All right. So let's begin with this chapter 7. Okay. So let's take a look at the next slide. Okay. So the learning outcomes. Okay. So at the end of this class, okay, all of you should be able to, okay, explain the different techniques for placing file records on disk. Okay. And the second learning outcome, okay, all of you should be able to give an examples of application of primary or clustering and secondary or clustering indexes. Okay, so that's the second learning outcome. Okay, the third learning outcome here, all of you should be able to, okay, distinguish between the non-dense index and a dense index. Okay, fourth one will be we all should be able to use the dynamic multi-level indexes using the V plus 3. Okay, the V plus 3. And then fifth one is all of you should be able to explain the theory of hashing techniques. And last will be all of you able to use the hashing to facilitate dynamic file expansion. So these are all the learning outcomes for this chapter 7. Okay, so when you finish all this lecture, all of you should be able to do all these things. Okay, you should be able to understand all this. Okay, so without wasting any time, let's go to the next page. Okay, so for the introduction over here, okay, we know that the database is stored as a collection of files. Okay, collection of files. Okay, so the main issue is addressed generally in the physical design. Okay, in a physical design. Okay, so how do we store files in a physical way? Okay, because you need the storage media. Okay, and this file organization. Okay, there are some many alternatives exist. Okay, each appropriate in some situation based on situation how to organize the file. Okay, it depends on the situation. Okay, some of the situation might be okay to use this type of file organization, some are not. Okay, it depends on the situation. Okay, and indexes, how to index all those files. Okay, so that's some of the main issue. Okay, addressed generally in the physical design. Okay, so the third point over here, changing, okay, or deleting, inserting, or updating. Okay, the database. Okay, it requires maintaining the file structures, updating indexes. Okay, all right. So let's move to the second. Okay, sorry, not the second. The next slide. All right. All right. So we look at the file organization. There will be a key sequential of hash. Okay, there are three things over there, and for indexing structures, okay, there will be a hash index, P plus 3 index, if-net index, and join index. Okay, so these are important, okay, for the database. Okay, so you just have to understand truly about this. All right. Next, look at the storage and file structures. Okay, so what we have over here is, okay, the database is store is a collection of files. So this one, I need all you guys know. Okay, the database used for store a collection of files. Okay, so each of these file, okay, is a sequence record. Okay, there is a sequence numbering. It can be numbering or other than numbering, but in a sequence. Okay, you can see over here a picture. It's starting from record 0 up until record 11. You need to say it's all in sequence. Okay, starting from 0 up until 11. It can be more records. Okay, and generally, okay, a separate file is used to store records of a relation. Okay, they are separate file. Okay, so these records are either fixed size or variable size. Okay, fixed size meaning to say the size is fixed, and the other one variable size because the size might be changing at one time. Okay, it can be at one time or keep on changing. Okay, variable size can be any size certain. Okay, so if you look at this picture below here, that is the example of the fixed size records. It's fixed and it doesn't change. Right? So let's take a look at the next slide. Okay, the variable length record. Okay, so what is a variable length record? Okay, so this variable length record arises in the database system in a several ways. Okay, so you can see over here there are 4 things. Okay, which is one or more fields have variable length, or one or more fields are repeating. Okay, okay, repeating the same thing. Okay, one or more fields are optional. Optional. Okay, we use or not to use. Okay, and file content records of different types. Okay, so the representation of a record with a variable length attributes. Okay, so this one is typically has 2 parts. Okay, there are 2 parts in it. Okay, initial part with fixed length attribute. Okay, and it's followed by data for variable length. Okay, attributes. All right. So talk about fixed length attributes. Okay, such as numeric value, okay, number, the dates, or the fixed length character string. Okay, are allocated as many bytes as required. Okay, to store their value. Okay, that one is a fixed length. Okay, so a variable length attributes, okay, can be a variable character types. Okay, the var, okay, are represented in the initial parts, okay, of the record by a pair. Okay, the pair could be offset and length. Okay, so when the offset denotes where the data of for that attribute begin within the records. Okay, sorry, record. Okay? And the length, okay, the length, okay, is the length in bytes, correct, of the variable size attribute. Alright, so the value for this attribute are stored, okay, consecutively. Okay, so after the initial fixed length part of the record, okay, the initial part of the record store of fixed size, okay, of information about each attribute, okay, whether it's fixed or variable. Okay, so that's some of it. Okay. So some of the variable length record and the fixed length record. Okay. Take a look at the next slide. If we look at this file organization, okay, so what is file organization? Is a method of arranging a file of record on external storage, other storage, external, okay, not internal but external of other places, okay. So there will be a heap, sequential, and hash file, okay. So if you look at the heap, it's in unordered files, okay. So records are placed on the disk in no particular order, okay. We just put it like that, okay. So new records are inserted at the end of the file, okay. So anything comes here, they will put at the end of the file. So you can say they keep on adding at the back, okay. That's why they call it unordered, okay. Heap files, okay. For sequential file, this one in order, okay. Records are ordered by the value of a specific field, okay. It depends on what the field you're going to um, make it in order. It can be by ID, it can be names, okay. Maybe it can be mm, yeah, the numbering, okay, can be like that. Okay, for hash file, okay, records are placed on disk according to a hash function. Okay, there is a function hash which will automatically order the file. Okay, place the file where to be stored. Okay, so you can look at here, the heap, they are sequential, they are hash file. Okay, so that is some method of arranging in the external storage. So just keep in mind there only three method. Okay, so heap, sequential, hash. Okay, so if heap, okay, is an unordered, anything that come in for store, they will put at the back. Okay, for sequential, they will put it in a sequential way. Okay, by name, or it can be by any value. Okay, it depends on what field you are going to use as a sequential file. I mean to say, sequential in ordering all those records. Okay, for hash file, of course, there are record placed on this according to the hash tag. It depends on the function and how it works. Okay, so yeah, let's take a look at the next one. Okay, so now you can look at here. Okay, the heap file and the sequential file. Okay, so heap file, like the previous slide, okay, it says that it's an unordered file. Okay, so anything new coming in, they will put at the back or at the bottom. Okay, so when we look at this one, okay, it doesn't order in a proper way. Okay, A dash 217, A dash 101. Okay, it does not put it in an order. Okay, but when we look at the sequential file, okay, this one is ordered by this value, okay, this numbering. Okay, so we can look at here, starting from, might be this one is an ID. Okay. If it's an ID, then we will place the one with the a smaller number will be at the top. Okay, so we can see here 10101, and then next is 12121, and as we look at the bottom, the number grow. Okay, so yeah, we can predict this one, the sequential file, are using this type of numbering as the key. Right? It doesn't follow this one, but it follow on this value. Okay, the lower value will be at the top, and the higher value will be at the bottom. Okay, That is the sequential file. And this one are the heap file. So far, do you guys able to understand on this? Oh, is it my voice quite tenggelam? I thought everything is okay. Okay, so let me put this microphone a bit near. So far, is it okay? Are you guys clear to hear? Is it okay now? Oh, okay. Noel, is it you are the only one who unable to hear my voice clearly? The rest, are you guys? Can you just hear my voice clearly? Or only Noel? Okay, 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 okay. Don't worry also, okay, Noel, okay, because everything here will be recorded. Okay, okay, okay. Thank you for the feedback also. But don't worry, everything here will be recorded, so you guys can watch it again later on. Okay? Don't worry also, Noel, okay? I will upload this video also later on. Alright, so you can look back. Okay? And so far, everything is okay with this heap file and sequential file. Alright, thank you. Okay, so we're going to continue, okay? So, yeah, we'll just continue a bit and then we take a break, right? Okay, so let's proceed with this one. And this is other hash file. Okay. So what are the difference between the heap file, sequential file, and the hash file? Okay, so we look at this one. Okay, we just look at this picture first. Okay, the key will be the flyer, and then they get into the hashing algorithm. Okay, hashing algorithm means to say there is a way of to do the hashing. Okay, okay, and then they put it in the relative record numbers. Okay, okay. So this hashing algorithm, okay, is a routine. Okay, is a routine that convert a primary key will be the flyers, okay, into a record address. Here, record address is this one. Okay, so although there are several variation of hash file, so in most cases, okay, the records are located non-sequentially. Okay, it's a non-sequentially. That is not in order lah. Okay, but okay, the sequential data processing is impractical. Okay, sequential data processing also is impractical. Okay, impractical also. Okay, so okay, a typical okay, sorry, yeah, this one. Okay, a typical hashing algorithms. Okay, a typical hashing algorithm. Okay, it is the techniques of dividing each primary key. Okay, by its value. Okay, by a suitable prime number. Okay, and then using the remainder of the division, okay, the division, okay, as the relative storage location, okay, on the storage location. Okay. So, okay, so here I can give an example of it. Okay, so let's take an example. Okay, suppose okay that an organization, this one organization, okay, they has set approximately okay, so 1,000 employee records. Okay, 1,000 employee records to be stored on a magnetic disk. So this magnetic disk because it's hard disk. Okay, HDD. Okay, so a suitable prime would be 997. Okay, why is 997? Because it's close to 1,000. Okay, so that is the prime number. Okay, so now consider that the record of the employee ID, okay, the employee ID is 12396. Okay, let's say it's 12396. Okay, So when we divide this number by 997, okay, 997 is the prime number, okay, the remainder is 432, okay. We divided, okay, the number, okay, from the 12396,997, okay, the remainder is 432. So the remainder number, the 432, okay, will be stored in a location of 432 files. 432 file means that might be in the box of 432. We will insert those ID of 12396. Okay, so that is an example of hashing. Okay, just an example, okay, because this hashing algorithm has a lot of mathematical things happen inside it, okay, or how they calculate everything to put those ID into a certain location, okay, in the hard disk. Okay, they have a lot way of this algorithm works. Okay, so maybe we can look at this one. Okay, this example of hashing. Okay, so we look at this example of hashing. Okay, so let's assume a table with X slot. Okay, X slot means say these are the slot. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, of course, in a computer they will start with 0 as a number. Okay, for a normal user, okay, 0 means nothing. But for electronic electronic things, okay, computer, 0 is a number. It's the first number. That's why it starts with 0. And altogether, this one total of 8 slot. Okay, because we counted from 0 up to 7. Okay, so like that example of this hash key. Okay, so the key, okay, the percentage value, and then the table size. Okay, the table size of course is 8. Okay, 8 slot. Okay, so just assume like this one. Okay, so 4 here meaning to say is the location. Okay, is the slot. Okay, so it can be this number 56 with the at in the at slot will be at the fourth, not the fourth, this is on the fifth. Okay? The fifth slot. Okay, so 1, 2, 3, 4, 5. It will be located at this one. Okay, the 56 will be in the fourth slot. So this one is the fifth slot. Okay? Fifth slot. Okay, because this one is 1, 2, 3, 4, 5. Okay, and for this one, this number 18 will be at the second or the third slot. Actually, this one is a third slot. This one is the first one, second, and third. And for this number 72, the key of 72 will get into this 0 in the first slot. And for key 43, will get into the fourth slot. Okay, so don't get confused when I say fourth, because this number 3 represents the fourth slot in 1, 2, 3, and 4. And of course, the key 6 will be into the seventh slot here. Okay, so these are the example of hashing. Okay, example only. Okay, so when we assume that they are only X slope. Okay, so that's how it works actually. Okay, okay, so your key value are not sequential actually. Okay, they will be randomly put inside the slot. Okay, so far you guys understand?
Sensei.
Yeah.
Uh, is the 7236, is that the data or a key?
Oh, it's a key.
Oh,
All right. All right. I think yeah, it's already 9:50, so let's take a break about 10 minutes and we continue with this chapter 7. Okay. next slide. All right, so we just took about 10 minutes break and then we continue that. All right, all right. See you guys in 10 minutes. Yeah, Alvin.
Sir, the chapter 7 you have published in the Google Classroom.
What again, Alvin?
The chapter 7 you have published in the Google Classroom. The chapter 7.
Chapter 7. Is it not in the...
Yes, I checked like thing like no for me.
Oh, not for me. Okay, let me check first, okay, whether it's in or not. Let me check first, okay. Oh, sorry, it's not in yet. Yeah,
Okay,
I
okay.
post it, okay. Never mind, after the class, then I post it, okay?
Okay.
All right. Hold on, just give me a minute first. Okay, so let's continue. Okay, so we have 59 of slide for this chapter 7, okay? So, yeah, we're going to cover might be half of it, okay? See how, okay? Okay, so let's moving into the next slide. Okay, so we're getting into the indexes. Okay, so what indexes? Okay, indexes I believe we cover in chapter 6, okay, some of it in chapter 6, okay. So let's take a look at the B plus 3 indexes, okay. So the B plus indexes, okay, is the most common types of index used in the databases, okay. It's the most used and because it's a common type used in every databases, okay. And second one, the hash indexes, it is a group for simple and fast lookup operation. Okay, so we use the indexes. The hash indexer is only used for this one fast lookup, lah. Okay, fast searching. Okay, to look for the information. Okay, and the bitmap indexes used in the data warehouse application. Okay, used in the data warehouse application. And last one is the joint indexes. Okay, so the joint indexes common also for the data way application. Okay, so we look at the data warehouse. There are two indexes mostly being used, which is the bitmap and the joint indexes. Alright. Okay, we're going to look at one by one of the indexes. But first, let's take a look at the next slide. The index evaluation matrix. Okay, we look at the matrix. Okay. Access time. Okay, how fast it can be accessed. Okay, so the equality of searches. Okay, it records with a specified value in an attribute. That is the equality searches. Okay, for the range searches, okay, it records with an attribute value falling within a specific range. So you can differentiate those two. Okay, for equality searches, okay, all the records, okay, with a specified value in an attribute. But for the range, okay, the record with the attribute value falling within a specific range. We need to specify the range, okay, for the searches. And this one will be how to say, yeah, for the access time, okay, how fast we can access. Okay. For the insertion time, okay, time to find correct place to insert the new data item, plus with the update the index structure. Deletion time, Okay, time to find the item to be deleted, plus update the index structure. Okay, and then the last one will be the space overhead. Yeah, space overhead, space to store the index structure. Okay, so these are the evaluation metric index. The index evaluation metric. Okay. So we have access time, you have the insertion time, you have the deletion time, you have the space overhead. So you can look at here the each of the meaning of it. Okay. So yeah, if you look at the insertion time, again, it's a time to find the correct place. Okay, delete, first to find and delete those items. And space overhead is a space to store the index structure. Okay, need the space for the index structure. If it's no space there, not able to the index. Okay, so let's move to the next slide. Classification of indexes. Okay. So they are clustering versus non-clustering, and the other one is dense versus sparse index. So we take a look at the first one, clustering index. Okay, it's an ordering of index, nature's ordering of values of such key attribute in the file. Okay, so that one is the clustering. Okay, for the dense, okay, every value of the search key attribute found in the table also appear in the index. Okay, anything that you search, okay, if it match with the keywords that you're putting, okay, let's say you put it the value of, let's say we take a name of Albert. Okay, then anything that come with Albert, it will appear. Okay, that's one of the example of it. Okay, now let's take a look at the next slide. Okay. So the dense index, okay, and index records appear for every search key value in the file. Okay. So now let's take a look at this picture. Say when you look for 101010, they will show you this 1010. Okay, and they take all of this information, okay, so that we're able to see. Okay, from the value of 10101, okay, it will appear this information. For 1212, they will put all of this to show you. Okay, and with this one, okay, biology, okay, they will look for all the biology. Okay, like the computer science here, like computer science, they will appear all the computer science value. Okay, the key value over here. Okay, same goes to the electronic engineering. It's only one, then it all will appear one. Okay, like finance also we have two over here, then they will show you the finance. History, of course, they will put it all the history all together. Music, and physics. Okay, physics. Okay, they all been ordered according to this key value. Okay, so that is the dense index. Okay. When you look at this one, following by the sequential index, okay, we just put it this numbering in order. But when you look at this key value over here, this one would be what we call it, history, physics, music. This one might be this kind of table, main table of this. Okay. Might be this one, field. Okay. Field of computer science, field of finance, music, physics, history. Okay. name of this column can be developed. Okay, so the big key value of this column it can be the computer science, finance, music, so on. And you get order like this one: biology, computer science, electronic engineering, finance, history, music, and physics. Then it will be appear like this. Okay, when you order those according to the field value. Okay, so when if you put this one first electronic engineering, that will put it the electronic engineering first, then followed by the rest. Okay, so they will put according to what you are searching here. Okay, biology, then biology, they will sort all the biology first, computer science, electronic engineering, finance, history, music, and physics. If there is only one, then it will appear like this one, only one biology, okay, according to the field. Okay, so let's take a look at the next one. This will be the sparse index. Okay, so this sparse index, okay, it contains index records for only some search key value. What are the some search key values? Look at this one. Okay, to locate a record with the search key value, okay, K, we, okay, need to find an index record with the largest search key value. Okay, and then the second one, search file sequentially starting at the record to which the index point. Okay. So it's similar also. Okay, from 1010, 32343, 76766, then they will appear this one. And they will took this one out, this one, this one. Okay, just like that. Okay, pass index. Let's take a look at the next one, next slide. Okay, compare two dense indices. Okay, so this sparse index we compare with the dense. Okay, so it more less space and less maintenance overhead for insertion and deletion. Okay, in this case, sparse index. Okay, so with dense index, when a file is modified, okay, with alter, okay, modified any changes, okay, every index on the file must be updated. Okay, this is with dense index. Okay, so updating indices imposes okay, overhead on database modification. So generally with this, okay, it's slower than dense index for locating records. Okay, generally slower than dense index for locating records. Okay, for this sparse index, I mean to say dense index is much more faster for locating, okay, to search for the things, okay, that you're going to search for. But the good trade-off here, sparse index with the index entry for every block in the file corresponding the the least search key value in the block. Okay. Right. Okay. You look at this one. Okay. The sparse index and index entry for every block. Okay. There is a block. Okay. In the sparse index. Okay. It corresponding to least search key value in the block. So yeah. It will be look like this one. Okay, so if this one is a block 0, this one is block 1, okay. So it will look corresponding, to me, to say responding to the research. Okay, So yeah, that is sparse index. Okay, so when we're moving into the non-clustering index, okay, so this one is a non-clustering index. So clustering index, the ordering of the index matches ordering of values of search key attributes in files. Okay, so we can see here. Okay, the first point here it says that frequently one wants to find all the record with value in a certain field. Okay, and the file is not ordered on the field. Okay, you're looking for the certain field, but the field is not in order. Okay, you can look at the example number 1 here. In the instructor relation store sequentially by ID. Okay, find all instructors in a particular department. You can see the example of number 1. Okay, it says that the instructor, this instructor, okay, store sequentially by ID. Okay, they all been stored according to the ID. Okay, sequentially. Okay, but in a different department. Okay, for the department field, okay, will be different. Okay, so example number 2 here, find all instructor with a specified, okay, salary or with salary in a specific range of value. So that is the example of number 2. Okay, so example number 1, we want all of this instructor. Let's say this is the instructor, okay, and these are the ID. Okay, so the ID will be in sequence, and the department is not in order. Okay, you can see Sri Nivasan is from the computer science, okay, and Tats also from the computer science, and Grant from the computer science. So this one is not in order. Okay, they are ordered according to the sequential. Okay, so find all instructor with the specified salary. So this one might be the salary. Okay, in the specific range of value. Okay, so it will be looks like this one. Okay, find all instructor with the specified salary or salary in the specific, okay, specified range of value. So these are the range of salary. Okay, they're going to sort. Okay, they're going to make an order of this one. So they will put it like this. Took all this first one into this. Okay, they will pick this one, Mozart, starting with 40,000, 40k, 60,000 will be 60,000. Okay, and Said, okay, like that. How it find all this instructor, okay, according to this salary field. Okay, one. Okay, so that is non-clustering index. Okay, so yeah, next one is still in the non-clustering indexes. Okay, so a non-clustering index must have an index record for every search key value. Okay, they must have this one. Okay, so the key index record point to a bucket contains pointers, okay, to all the actual records with the particular search key value. Okay, so the bucket structure, okay, we look at the these yellow boxes over here. Okay, the bucket structure is used to search key is not primary key, and file is not sorted in a search key order. Okay, it will not be sorted in a search key order, but instead, okay, it will search according to what you are to search, okay, according to the range of this salary. Okay, sort out in that. In the sound, okay, according to the salary range. Okay, you can put it each of this bucket. Okay, so they will sort out according to this one now. Okay, for the non-clustering indices. Okay, let's moving into the next slide. Okay, so here we are able to look at those two clustering and the non-clustering index. Okay, we look at the yellow boxes over here. It says that the clustering index, okay, ordering of index matches ordering of values of the key attribute in file. Okay, and this one, okay, it clustering indexes can be sparse, since it is always possible to find records with the intermediate search key value. Okay, and the non-clustering indexes have to be dense. Clustering, sparse, non-clustering, dense. Okay, it matches them. This is the clustering index. Because we look at the cluster. Okay, the 1010, this 1010, 32343, 34243, 76766, okay, the 76766. Okay. So the non-clustering index will be like this way. Okay. Take a look at the next one. Clustering and non-clustering. Okay. So the sequential scan using the clustering index is efficient. Okay, but the sequential scan using a non-clustering index is expensive. Okay. It says here the sequential scan means to say, yeah, scan with the sequence ID number. Okay. But sequential scan using a non-clustering index is expensive. Say those numbering are not in order now. Okay. This one will be the clustering index, because every one of it will be in the same sequence. For the non-clustering index will be like this. Okay. This one is not in the sequence. Okay. And yet we are looking for a sequence like this. Okay. This one we are going to do the sequential scan. The sequence scan means to say from this range of salary according to the numbering. Okay. The lower will be the first one and the higher will be the last one. Okay. So the scan sequentially in a non-sequential value or non-clustering index. Okay, because the index will be in this one and not according to the salary. Okay. Alright. So let's move to the next one. Okay, multi-level index. So before we move into this multi-level index, um, here we are going to take a break another 10 more minutes. Okay. So each every 30 minutes we have a break. Okay, because yeah, I know that none of us can handle straight 2 hours of lecture. Okay, we need some time to get refreshed. Okay, so yeah, we're going to continue back with this multi-level index after 10 minutes break. Okay, so we see you guys 10 minutes after. It will be 10:15. Okay, let's take a break, everyone. All right, so let's continue. All right, so we're going to continue with the lesson, okay? So I guess ready? Yeah, so I assume everyone is here, everyone is ready. Yeah, Noel. Okay, all right. Okay, since everyone is ready, so we will start. Okay, so we look at this one, multi-level index. So at the blue box over there, okay, look at it. Us to imagine this, okay? A file of 100,000 records, okay? So each 10 of the records is in one block, okay? So the sparse index, okay, equal or more one index record per block. So how many records will the index have? Okay, that is the question. Okay, how many records will the index have? Okay, so 100,000 records. Okay, 10 records in one block. So each 10 record will be in one block, and one index record per block. So how many blocks do we have? Okay, 10. 100,000 divided by 10. This one will be how many? 1,000 blocks. Okay, so each block will have one index. So how many records? Okay, will be the index have. So one index record per block. So per block will be having 10 records only. So how many records will the index have? Only one. Okay, per block. So index records are smaller than the data record. Okay, look at this one. Okay, index records are smaller than the data record. If 100 index record fit into one block, how many blocks will be needed to store the index? Okay, so everything will be here. Okay, the 100,000 okay, divided by the 10 blocks to store the data records. Okay, and this one there will be 10,000 index records, and the index will require 100 blocks. Okay, so we're moving into the next slide. Okay, so if an index does not fit in the memory, the access becomes expensive. Expensive means very slow. Okay, there's not enough memory. So to reduce number of these accesses to the index record, okay, construct will be the outer index and the inner index. So the outer index will be the sparse index or the main index, and the inner index will be the main index file. Okay. So outer index is a sparse index on a main index, and then the main index will be the inner index. Okay. So if even the outer index is too large to fit in the main memory, yet another level of index can be created or so on. Okay. So if it cannot fit, then create another one, create another level of index. So it will not become expensive. Okay. And indices, all levels must be updated on insertion or deletion from the file. Okay. So let's take a look at the example of this multi-level index. Okay, it is in the next slide. Okay. So you can see here the example of multi-level of index. Okay. You look at here, there are two levels. Okay, the second top level, okay, you can see this block divided into another block, into another block. Okay. See over here, this block, there's another block, there's another block. Okay, the primary key field will be in the data file. Okay, there. Okay. You can see there are two levels of index. Index, then the data files. Okay. Index, and the data file. Okay. The top level going into the base level and to the data file. So that is the example of how you look at the multi-level index. Okay. From the top level going down to the lower level, then to the specific data file. Okay. So, example, like you are looking at the number file key field. Okay, you look at this at the top first. So you look at 2 because these 2 might be in the range of some number. Okay, here they will straight away look at this going to the first base because they're looking straight away to all of this number. Okay, and it will require a certain amount of time to search for the key. Okay, so to make it more faster, you got it into a certain block and to find it more faster. Okay, it's like you have example like one brain, you have another 4 brain inside. Okay, to work together to search for the key file. Okay, the data file. Okay, there's nothing rather than one brain to look at all of this one. Okay, for example here, okay, at one brain to divide it into 4, so each of it will look at the, let's say, primary key of 5. Okay, so when they divide it into the 4 brains, okay, so each brain will works together, okay, at the same time. So we know that the second, the third, and the fourth brain doesn't have the primary key field of 5, so this one will automatically deny the search. Okay, and because this one will be the one to find this primary key of 5. Okay, of 5. Okay, so that is an example of multi-level index. Okay, so we're moving into the next one. Okay, so now we look at this P plus 3 index files. Okay, so the B plus 3 must satisfy the following properties. Okay, the properties need to be met. Okay, so all paths from root to leaf are on the same link. Okay, and each of the node that is not a root or a leaf or a non-leaf node has been as between. So this is the formula n divided to n children, where the n is the maximum number of pointers per node. Okay, so n is fixed for a particular tree. Okay, so a leaf node has between this one. That is our formula. N, the maximum number of pointer node, minus the 1. Okay, total of this, or result of this will be divided into 2. Okay, so special cases, if the root is not a leaf, it has at least 2 children. 2 children represent the leaf. If the root is a leaf, that is, there are no other nodes in the tree. So the value can be between 0 and just 1 leaf. So you can look at these pictures. Okay, at the top here will be the root node. Okay, will be the root node. Okay, down here will be the internal, and from this internal we have another down here which we call it a leaf nodes. So I think we might look at the next page for clearly. Hold on. Okay. Example of b plus 3 of order 6. Okay. N equal with 6. Look at here. Okay. 1, 2, 3, 4, 5, 6. Okay. We must have 6 also over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Okay. So it's a bit, this is an example of a B3 for instructor file. Okay. N equal 6. Okay. So the leaf node, okay, the leaf node from here must have between 2 and 5 value. Now it's 2 and 5 value because of this one. Okay. By looking at this one. Okay, so the non-leaf nodes other than root must have 3 and 6 children. Okay, look at this one. N divided by 2 and N with an N6. Okay, in 3 and 6. So that's why you get N is 6 divided by 2, and of course we get 3. So the root must have at least 2 children. And so this one might be confusing, okay, on how it getting all of those things, but I believe in the next example you are able to see. Okay. Yeah, the root must have at least 2 children. Here it shows that you have 3 children, 1, 2, and 3. Okay. So let's take a look again at what does it mean with this formula n minus 1. Okay, to make it more clearly. Okay, so back to the previous page. Okay, look at this one again. Okay, so all parts from root to leaf are on the same length. Same length, you say this length. Each node that is not a root, okay, so this one is a root and not a root or leaf would be in this one. Okay, each node that is not a root or a leaf has between n divided by 2. And the n children, where n is the maximum number of pointer per node. Pointer, okay, pointer will be the 1, 2, 3, and 4. Okay. Okay. So this one, maybe there are 4 pointer. Okay, 1, 2, 3, and 4. Okay. N is the maximum number of pointers per node. Okay. N is fixed for a particular tree. So there are 4. Okay, so since that is 1, 2, 3, okay, all okay is 4. Okay, so there are 4 pointers. So special cases, okay, if the root is not a leaf, this root is not a leaf because it's not a leaf, okay, and it has at least 2 children like this one. Okay, if the root is a leaf, then that is there is no other nodes in the tree. Okay, when this one are no other root in the tree, it can have to be can have between 0 and n minus 1 value. Okay, so this one might be a bit difficult to understand unless you've done those indexes in practicals too, and you might be able to understand this one more clearly. Okay. Okay, so when we look at this one again, okay, the n equal with 6 because there are 6 pointer 1, 2, 3, 4, 5, 6, just because in this, what we call it, this one is the length, okay? And just because of the length, we only have 3 children, okay? 1, 2, and 3, and each of these children have their own, yeah, okay, their own pointer over here, because there will be a 6 as well. This one will be leaf, this one will be the root. Now it can be this one, the intermediate level. Sorry, not intermediate, the internal nodes. Alright. So of course this one is like being confused, okay, the leaf node, okay, the leaf nodes, these are the leaf nodes, okay, must have between 3 and 5 leaf. Okay. Non-leaf, so where is the non-leaf? Non-leaf will be this one. Okay, and the root must have at least 2 children, but for this one, I have 1, 2, and 3. Okay. So let's take a look at the next one, next example. Okay, so these are the b plus 3 more example. Okay, so we can look at here from the root node down to the internal nodes, down to the leaf nodes, and from the leaf node to the specific, and all of this table. Look at this one, the Mozart, look at the root node, this Mozart, you can see Mozart is over here. See this Srivasan, okay, and over here is Einstein, the Einstein over here is this sign. So we must put it like this one. Okay, so Srivasan, okay, the leaf node have this Mozart also, have this C, Srivasan, Wu, okay, on this Einstein, and gold, and brown, and this is what we call the Calipari, Creek, Einstein, Ivy. So these are the example of indexes, okay, of B plus 3. Okay, from the root, and then you divided the root, getting into the internal node, from the internal nodes, getting into the leaf node, and from this table. And this is index according to the name. Okay. So this is only an example of the B plus 3. Okay. There's nothing to be calculated over here. So let's take a look at the next page, the balance tree. Okay. So a B plus 3 needs to be balanced. Okay. Meaning that all of its leaf nodes are at the same level. But when you look at this picture, it's an unbalanced tree because the right side over here has more leaf nodes. Okay. It's not balanced. Okay. If it has more on this side, on the right side, okay, and it's not balanced with the left side. Okay. So keeping a tree balance is important to guarantee that no nodes will be very high level and hence it require many block access during the research. Okay. So that's why we need to keep it balanced. If it's not, then we have to look at here, look at here, look at here, look at here. There will be too many of leaf level, okay, on to get to those item. Okay, so that's why you need to balance those three. You are using the B plus 3 indexes. Okay, and let's check the next one. These are the B plus 3 node structure. Okay, so you can see here there is a P1, K1, P2, KPN, minus 1, KN, minus 1, PN. Okay, so we look at this one first. Okay, so the K are the search key values. Okay, the K are the search key value, and the P are the pointers to a children. And this is for non-leaf nodes. Non-leaf node is the root or pointer to the records or bucket of records. Okay, this one for the leaf. Pointer of the children will be the root. Okay, so the search key in a node are ordered. Okay, so you can see K1 less than K2 less than K3 less than up until K less than N less 1. Okay, this one might be confusing. Okay, one will be confusing. Okay, but no worry. Okay, we're going through one by one. Okay. Look into the next page. And look here for the I is equal to 1, 2, and so on, and minus 1. Okay, the pointer points to a file record with search key value of K. Okay. So if the L, okay, L are leaf nodes and I less than J, L's search key value are less than or equal to L search key value. Okay, so this one must be continued. What are this all about? Okay. This is all how it points to the nodes. Okay. So root node here, the internal, the root and all have their own value. Okay. This one might be continued. Okay, we are not going to do all these things also. So this is only your knowledge for it. Okay. And let's take a look at the next slide. Okay. Here we look at the non-leaf nodes in the P plus 3. Okay, for a non-leaf node with n pointers, okay, so all the search keys in the subtree to which the P, okay, the P, okay, points are less than the K. Okay, example on the left subtree, and all the search key in the subtree to which P points are greater than or equal to K. So the right subtree. Okay, these are only the example of the K less, okay, in the point, then it will be the left, higher or equal will be at the right. Okay, it will be divided like that. Okay, for the non-leaf nodes with in pointer. Okay, so far, yeah, that's it. Okay. So now let's take a look at the next page. Queries on the B plus 3. Okay, how the queries work. Okay, so it starts with the root node. Okay, so root node, we know that the root node will be at the top over here. Okay, then examine the node for the smallest key value. Okay, so it will be smaller k value. So if such a value exists, we assume it is k, then followed by the pointer to the child node. Okay, if it not exist, then you can see over here Okay, k is greater or equal to k m minus 1, n minus 1 here, where there are m pointer in the node and follow p m to the child node. Okay, so here, if the nodes reached by following the pointer above is not a leaf node, then it will repeat the above procedure on the node. Okay, and follow the corresponding pointer. Okay, you want doing the same thing. It's not a leaf node. Okay, so eventually reach a leaf node. If the key ki is equal to k, it will follow the pointer pi to the desired records or bucket. Okay, and else no record with search key value k exists. Okay, so it will be next slide here. This one. Okay, root, kernels, and leaf node. Here select from the structure where the structure L name is in. So when you do this one, this command, then it will query following this D3. Alright, so I believe for today lecture I will stop at this point, okay, and we will continue the lecture next week. Okay. Are you guys okay with this? Alright. Okay, so we'll be having our practical this coming Friday. Okay, before that I need to know, okay, your practical, you all stop at which part? Is it still in the, is it practical 4? Have you done the practical 4? I believe it's practical 5. Okay, have you done the practical 5? Last time is, yeah, practical 5, page 7. Okay. So I'm going to continue from practical 5, page 7 this coming Friday. Okay, next class. Okay, yeah, continue on page 8. Okay, we try to do it faster, okay, because last week we already took our practical time for your midterm test. Okay, so yeah, okay, we can do it faster this Friday. Okay, I forgot to ask you guys, so how's your exam last week? Your test? Is it okay? Everyone is okay? Easy for you guys? Yeah, no problem. Everything is easy. Huh? As long as you study, you understand the content, everything should be okay, no problem. Okay, might be the problem is the time, okay? Using time to do that one. Okay, maybe you are given less time to do it was only 1.5 hours, okay? To do that one, and then you need to upload again, okay, take a picture, okay? That one might take some of the time, okay? But overall it's okay. Yeah, okay lah. Alright, so don't worry, this video will be uploaded, if not by today, then yeah, maybe tomorrow morning. Okay, so thank you everyone. That's all for today. Thank you for listening to this lecture. Hope everything is good for you guys. Stay safe wherever you are. Okay, and thank you.